Alright, hey physics class. This is video for chapter 24, Magnetism. The goal here is to supplement class Wednesday when I am not there, and then as a way for the people on Thursday who are missing class because they're field trip to get the information they need. So the plan is you're going to look through the PowerPoint slides without any video for that. You're just going to look through them, read the information, look at the diagrams, equations, etc. And then I'm going to go through this document, the guided notes, and all the questions. And I'm more or less just going to go through it and type in all the answers. But I'm doing it as a video and releasing it. That way I can kind of explain as I'm going what stuff is, and you might get more out of it by listening than just by reading the answer. So what is a permanent magnet? So I'm also going to color code the answers and then post this. So a permanent magnet is going to be a physical object. Oh, this is not a dark enough blue. Sorry, bear with me here. A physical object with magnetic properties that remain relatively constant. So you can change the properties through different means, but once you've set it up, it's going to stay as a magnet. It's not going to instantly revert. Kind of like a dipole. If it's a permanent dipole, it will stay as a dipole even if you leave it alone, versus an induced dipole is only a dipole when the inducing factor is nearby. Okay, so let me copy and paste here to get my color. Okay, a magnetic domain is a region of a magnet where the local magnetizations line up. Okay, so each little domain in a magnet will have a certain direction. And if all the domains are lined up, you get a permanent magnet. And if all the domains are pointing totally randomly, then you get something that is non-magnetic. Cool. Okay, what are the two poles of a magnet called? This is easy. They are north and south. The properties, so north kind of behaves like a positive charge. Kind of like I say, because it's not actually charge, and the key fundamental differences. So north is kind of like positive in that if you put a positive charge in an electric field, there's a force with the field, and a north pole feels a force in the direction of the magnetic field. So a positive charge feels a force in the direction of the electric field, and north pole feels a force in the direction of the magnetic field, and a south pole, feels a force in the opposite direction to the field. However, this is important, so we say however, magnets always come in pairs. I'll get more to that later because I have a specific question down here about it. So that's a key fundamental difference to the properties. And just like charges, I shouldn't say like charges, I should say similar to charges, opposite poles attract and like poles repel. So they have a lot of similarities to charges. Do they relate to positive and negative? So I'll say here kind of as above, but do not call the poles of a magnet positive or negative. The surest sign that you don't know what you're talking about is if you say the positive side of the magnet. If you just say that, everyone's going to cringe and know that you haven't really studied enough to master this topic. What magnetic field is created around a bar magnet? So, cool thing about magnetic field lines, because you can never separate the north and south poles, all magnetic field lines are closed loops. All magnetic field lines are closed loops. They don't start on one thing and end on the other. They continue through the object, but they do come out the north side of a magnet, wrap around, and go into the south side of the magnet. But inside the magnet, they continue from south to north to complete the closed loops. So that's pretty cool. How does the compass behave in a magnetic field? The compass, so a compass is just a tiny magnet. So the north side of the compass gets pulled with the field, and the south side of the compass gets pulled against the field. So the net force is 0, but the compass needle will rotate. So imagine if you've got something and you pull one end one way and the other end the other way. You're kind of like stretching it out, aligned with the forces. So the compass needle will rotate to be parallel with the field, with the north side pointing with the field. So a compass will tell you the direction of the magnetic field, and whichever way the north side of your compass is pointing is the direction that the magnetic field points at that location. So that's why they're useful in navigation, because of Earth's magnetic field. Can you separate the two poles? What happens if you try? So this is fundamentally the key difference between, well, one of the main key differences between magnetism and electricity. You cannot separate the north and south poles. If you cut a magnet in half, all you get is two smaller magnets, both with a north and south pole. And the reason here is, even though we draw the magnet and we label, like, we paint half of it red and say this is the south side, and we paint half of it blue and we say this is the north side, the reason is the overall magnetism is caused by the large number of little domains. So if you cut it in half, you still have a whole bunch of domains in the two pieces that you broke apart, and each of those little domains still has a direction, so it still therefore has a south and a north. And you can keep cutting them in half and cutting them in half and cutting them in half until you get down to a single domain. And even within a domain, if you cut that in half, you can get down to like individual little clusters of atoms that all have aligned magnetic moments. And when their magnetic moments are aligned, that gives you a north and a south side. If their magnetic moments are all misaligned, that gives you a net cancellation or zero magnetism. How does Earth's magnetic field behave? Okay, cool. So a couple of things I said here: strength, direction, and source. The strength is roughly 30 to 60 micro teslas. It's changing in strength because depending where you are, look at the picture in the slides and it will kind of make more sense. If you're close to where it's popping out of the poles, you're probably going to have a stronger field where the field lines are closer together. And when you're near the equator, you're going to have a weaker field where the field lines are spread out. It points geographically south to north. But, okay, so this is the kind of thing that throws people off. But that means the field lines come out of the geographic South Pole, okay, which means the geographic South Pole is the magnetic North Pole, right? Because the field lines come out of the magnetic north, so if they're popping out of the south and wrapping around, this is in the slide too, but I guess it's so important that I will draw a picture for you. Here is the Earth. You could think of Earth as having a bar magnet here. So this is geographically the South Pole and the North Pole. But let me put here geo south and geo north. However, because this is a magnetic north, then the field lines come out here, wrap around, and go in here, which is the south. And then, like I said before, inside they actually continue. They don't stop. They continue through. But the reason this is the way that we've designed our compasses and set up our system is because right here, if you have a compass, the needle is going to line up with the field, which means the needle is going to point that way. So the north side of the needle, right, the north side of the needle of the compass, is pointing geographically north. So we call this geographic north because it's which way the north side of the compass needle points. But the north side of the compass needle is attracted to magnetic south. Okay, so it's not super critical, and it's not the end of the world if you don't remember that, but it's kind of an interesting trivia fact, and it's easily explained through magnetic attraction. What is a symbol for magnetic fields, and what are the units? So maybe this would have been better to have earlier, but whatever. The symbol is a B, okay, a capital B. I know that that's annoying, that it's not a capital M, but after a while you just get used to it, and when you see B field, your brain just says magnetic field. And that's the way that these kind of things work. At first it's foreign and weird, and after you get used to it, you can't imagine it being anything else. The units are teslas, which is just a capital T, and 1 Tesla is huge. Okay, so when you're solving problems, usually the values are going to be pretty small. Like Earth's magnetic field, as you saw earlier, was just 30 to 60 microteslas. So a couple of Teslas is a massive, massive field. All right, let's move on. And so everything there in question 1, whatever those parts are, that's all about basically permanent magnets, so physical objects that have magnetic properties. So now we're going to see how this ties back together with electric current. And with electric current, it's going to get a little bit more complicated. We're going to get some equations, but it's really, even though it's more complicated, it's the fundamentally important idea, because it's how we create electricity, and it's how our entire modern civilization is based. So explore the relationships between electrical current and the magnetic field. So what sort of field is created by a current in a long straight wire? There's a lot of different ways that we can talk about this, but without a picture it's hard to say, so I'll just write down the answer, and you can look back on the slide if you need to. A long straight current carrying wire creates circular loops of magnetic field around it. They are strongest the closer you are to the wire, and they get linearly weaker as you get further away. So if you're twice as far away, the magnetic field is only half as strong, and they are concentric circles around the loop. For a picture, I'm not going to try to draw it here, just look in the lecture slides and you can see the picture there. There's an equation also, mu naught I over 2 pi r. That's in these notes, I think, at the end. Let's scroll down here. Yeah, there it is. Magnetic field of a wire is mu naught I over 2 pi r. This little mu naught is a universal constant. The value is listed in the notes, so go ahead and look it up there. It's 4 pi times 10 to the negative 7th. And yeah, so that lets you calculate the exact strength of the magnetic field near a wire. What is the equation for that strength? Oh, fancy that, fancy that. I'm going to just say here, see below, because I can't type all that fancy stuff. This is just an image. So your equation's there. What is the right-hand rule? Okay, so this is critically important to find direction. So all of these equations, they just get you the magnitude, and to get the direction, you're going to have a different right-hand rule depending on the scenario. So for this one, this is the magnetic field created by a wire. The magnetic field created by the wire. So here we go. Point your thumb of your right hand, so right hand because it's called the right-hand rule. Point your thumb of your right hand in the direction the current is flowing. Your fingers wrap around the wire in the direction of the B field. Okay, so they're concentric circles. So there's only two possibilities. They're clockwise or counterclockwise. So if you use your right hand with your thumb in the direction of the current and your fingers wrap around, that's going to be the direction the magnetic field points. What sort of field is created by a solenoid? So all a solenoid is a whole bunch of wires, long straight wires, that have been wrapped into circles or spirals. So this one, I'll just state the answer here and describe it hopefully in class, or you can get it from the pictures. The B field in a solenoid is constant inside and wraps around the outside. So I'll draw a little picture here. So if here's your solenoid, the magnetic field lines inside, they're basic, oops, that's not very good. So these are supposed to be constant parallel lines, all say pointing up, and then outside they wrap around. So interestingly enough, that should look familiar. This is nearly identical to what? Identical to a bar magnet. Okay, the key difference is that a solenoid is hollow inside, so you can do experiments in there because it's open space, whereas a bar magnet is obviously completely solid. What is an electromagnet? This is a coil of wire wrapped around an iron core, aka an iron core inserted into a solenoid. When current is turned on, there is a strong magnetic field inside that's amplified by the iron core. When the current is turned off, the induced magnetic field from that current goes away, and the iron core may stay slightly magnetized or return to a demagnetized state. So it depends on the materials that the core is made of, and it depends if it can be permanently magnetized or if it's just ferromagnetic material. That means ferromagnetic material means it can become magnetized, but it doesn't stay magnetized. So, and I guess also the iron core is optional. Just a coil still counts as an electromagnet. Yeah, that's true. So basically just a solenoid is an electromagnet. But I think you want to know kind of the idea here is it's a magnet. You're creating a magnet, but you're controlling it by the flow of electricity rather than having it be a permanent bar magnet. So basically you're creating a pseudo bar magnet that you can turn on and off with current, and that you can also control the strength of by putting more or less current through it. Alright, and the final third part of this here, let's see, we've got explore the relationship between magnetic fields and forces on charged particles. So just a quick summary. We talked about first properties of permanent magnets. Then we saw some properties how an electric current, or the flow of charge, will create a magnetic field around it. So clearly there's some kind of connection here between electricity and magnetism, and this last section here drives it home. So explore the relationship between magnetic fields and forces on a charged particle. So if you have a charge moving through a magnetic field, it will feel a force perpendicular to the direction it's moving and perpendicular to the B field. So how can it be perpendicular to both the magnetic field and the direction that it's moving? Well, it depends. So you have to use another right-hand rule. So we'll say, what is the right-hand rule? How does the direction come into play? So let me say two things. One is the particle motion must be somewhat across the direction of the field lines. So this means there must be at least a partial perpendicular component. If the charge is moving perfectly parallel to the B field, there will be zero force. So first of all, you only get a force when the charge is cutting across the field line. So the perpendicular component, so whatever piece of its motion is perpendicular to the field, that's the part that's going to cause a force. The larger that component is, the bigger the force. So the right-hand rule is a triad. So here it goes. There's three different ways you could do it because it's just a 1, 2, 3 orientation. So abstractly, you can say 1, 2, 3, 2, 3, 1, or 3, 1, 2. And you notice that those are all in the same order. 1, 2, 3. Let me get my color here. 1, 2, 3, or 2, 3, 1, or 3, 1, 2. All are equal. So sometimes the textbook or other things will have a different right-hand rule than what I'm explaining to you, but I guarantee you it's one of these three combinations. So the way that I personally do it is thumb equals direction the charge is moving. Then I say index finger equals magnetic field. Say the direction of, they're all directions, direction of magnetic field. And then let's say the FU finger, what's that one called? I guess the middle finger. Middle finger equals direction of force. This one you could also say aka open palm faces direction of force. I personally like to make an XYZ axis with my thumb, my index finger, and my middle finger. Kind of like I'm shooting a gun with my index finger straight out sideways. Let me draw it here. Sorry. It's the same one that's in the slide. So here's my thumb, here's my arm, here's my first finger, and then here's my middle finger, and then here's my other two, which are just wrapped into my fist. Wow, that looks pretty terrible, doesn't it? But this is the thumb, say, straight vertical, then my index finger parallel out, so this is like X, this is like Y, and then this one is perpendicular to both of those, so Z. So you're creating an X, Y, Z axis, and you're using them as follows. So thumb, index finger, middle finger, direction the charge is moving, the direction of the magnetic field, and the direction of the force. And that's very useful. If you forget this, you'll be able to calculate the value, but you wouldn't necessarily know which direction that it is going. So let's go back up to part A here. What force is exerted on a single charge moving through a B field? So again, it has to be cutting across the magnetic field, and the equation for this guy, if we zoom down to here, is magnetic force is QVB sine theta. So Q is the size of the charge, V is the velocity of the charge, B is the magnetic field strength, and then sine theta. So the angle here again is between the two vectors, the direction the charge is moving and the direction of the magnetic field. So if they're in the same direction, the angle between them is 0, and sine of 0 is 0. So again, if the velocity and the magnetic field are the same direction, meaning the charge is moving parallel to the field, then the force is going to be 0. And it's going to be maximum. Sine theta is maximum when theta is 90 degrees. So if the charge is moving perpendicular to the magnetic field, then you're going to get a maximum force. So I'll kind of emphasize that. You get a max force when charge is moving perpendicular to the field. And again, you get 0 force when charge is moving parallel to the field. Okay, what force is exerted on a wire carrying current in a magnetic field? So this is pretty cool because it's literally the exact same thing. A current carrying wire is really just a whole bunch of individual charges moving. Okay, so if the individual charges in a magnetic field get a force on them, then a current carrying wire will also get a force. Each charge gets a force, so overall the entire current carrying wire gets a force. And I'm typing pretty poorly here, aren't I? I apologize. Okay, and the right-hand rule is the same. The right-hand rule, RHR for short, is the same. We just use the thumb to mean the entire current. So instead of just a single charge moving, it's an entire current flowing through the wire, but the index finger is still the magnetic field, and the middle finger is still the direction of the force. And there's an equation for that as well. And the equation, let's make this a little bigger here. The equation is ILB sine theta. So it's kind of cool here. QV is a single charge moving at velocity v, and then IL is a current moving through a wire of length L. So if you know the flow of current and you know the size of the wire, that tells you the total amount of charges that are moving and how much they're moving. Just like if you have just one charge and you know the value of that charge and you know the velocity of that charge, you can figure out how much is moving there. So I think these two, if you know one, you pretty much know both. So if charges are moving, whether an individual charge or a whole current flow in a magnetic field, they're going to experience a force, and again, that force is perpendicular to their motion. So let me add or emphasize here, the force is always perpendicular to the direction of motion, and this is like important enough, I'm going to put it in all caps. This means the magnetic force is always trying to bend the path of the particles, but not speed them up or slow them down. So because the force is always perpendicular, right, a force parallel will speed you up or slow you down, but a force perpendicular will just try to change your direction. So magnetic fields, they don't do any work, they don't speed you up or slow you down. They're always perpendicular, so force times distance times cos theta is always 0, but they do always try to bend your path. So what you see is charges moving in magnetic fields always move in circles or spirals, and this is what creates things like the northern lights, aurora borealis, and stuff like that. So what happens if that wire is turned into a loop? This is complicated to explain, but pretty darn cool. And what happens is each side of the loop experiences its own force. Hold on.